Hello everybody, welcome into another lesson. So today we are going to start talking about inequalities in geometry. So up till now we've worked with equalities, everything being equal to something, which has made our lives easier. Well, for the next few lessons we're going to be talking about inequalities in geometry. And these are some properties from algebra that we are going to use in geometry as well. Some properties of inequalities. So if you have some arbitrary number a that's greater than a number b, so a is greater than b, and then you have another arbitrary number c that is greater than or equal to d, then a plus c is greater than b plus d. So that's one of the properties. Another one is if a is greater than b and that c is greater than 0, then a plus c is greater than b plus c. Well, that one definitely makes sense, because if you have a plus c, right, by one number, then you have b plus c, which c is the same number, and a was already greater than b, well then it makes sense that a plus c would be greater than b plus c. Now, also, if a is greater than b and c is greater than 0, then a times c is greater than b times c. That also makes a lot of sense. Then we have if a is greater than b and c is greater than 0, then a divided by c is greater than b divided by c. Then we also have if a is greater than b and this time c is less than 0, then AC is less than BC. The reason is because C would be a negative number, and when you have a negative, the bigger the number, we know when it's negative actually means it's smaller. So as we know, numbers work in reverse when we get to negative numbers. And then same thing with division. If a is greater than b and c is less than 0, then a divided by c would be less than b divided by c. Because again, when you work with negative numbers, the bigger the number, the smaller it actually is. And then let's see, if a is greater than b and b is greater than c, then a would be greater than c. Well, that makes sense. You could think of it like the transitive property for inequalities. That's kind of what I would think of that one. The transitive properties for inequalities. And then the last one we're going to hone on in here in a second with one theorem for today. If a equals b plus c, so it takes two numbers just to equal a, and c is greater than 0, then a is greater than b. That makes sense. If it takes something plus b to equal a, then a would have to be greater than b, right? Oh, I suppose, let's for example say 5 is equal to 4 plus 1, right? So 5 is your A, B is 4, C is 1. Well, it's true. 5 is definitely greater than 4. 5 is also greater than 1. It's greater than either one of those separately, but together you have an equality. So that actually makes a lot of sense. Now, there is one theorem today pertaining to triangles that deal with inequalities. And we're going to use it in some proofs today. This one is called the Exterior Angle Inequality Theorem. So yeah, that's a huge one, but it can be used in proofs, and we're going to use it in proofs today. So we have the Exterior Angle Inequality Theorem. What does that say? It says the measure of an exterior angle of a triangle is greater than the measure of either remote interior angle of the triangle. So first, let's talk about something before I read off this new theorem. Remember back when we were first learning about triangles, how we had a theorem that stated that the measure of the exterior angle of a triangle is equal to the sum of the two remote interior angles of the triangle. Well, this theorem ties in with that, the Exterior Angle Inequality Theorem. It states that the measure of an exterior angle of a triangle is greater than the measure of either remote interior angle of the triangle. It kind of goes back to the example I just did with 5 equals 4 plus 1, where 5 is greater than 4, 5 is greater than 1, but together 4 and 1 make 5. So let me draw a triangle to illustrate this point. We have a triangle, right? Here's the two remote interior angles, angles 1, 2, and then 3. Well, of course we know that the measure of angle 1 plus the measure of angle 2 equals the measure of angle 3, right? Because 1 and 2 are your two remote interior angles. Angle 3 is your exterior angle. So you combine the measures of 1 and 2 together, you'll get the measurement of angle 3. But the measure of angle 3 is greater than the measure of angle 1 itself. It's also greater than the measure of angle 2 by itself. That's what this theorem would be saying in relation to this diagram. So together 1 and 2 make angle 3, but angle 3 is greater than the measure of angle 1 by itself, and the measure of angle 3 is greater than the measure of angle 2 by itself. So that's the only new theorem we're learning today. We're going to do a few proofs that involve some inequalities. So let's go on here and do some of these. Let me draw some nice diagrams here. Alright, let's label these points here. K and L. Here's K and L. And then we have PM right here. So we have two triangles that are connected at point L, right? Here's what they give us. So we have been given that KL is greater than NL. We're also given that LM is greater than LP. What we have to prove out of this is that KM is greater than NP. That's what we ultimately have to prove, that KM is greater than NP. So let's go ahead and set up our columns here. Let's demonstrate an inequality proof. So let's set up our statements and our reasons. Of course, I think statement 1 will start with the given information that KL is greater than NL, and then that LM is greater than LP. Those were given to us. That's the reason. Alright, so then what's next? Well, isn't it true then that we can add up the sum of these segments and get the segments, right? So for step 2, we're going to say that KL plus LM equals KM. We can also say that NL plus LP equals NP. That's by the segment addition postulate. That still holds. So we have the segment addition postulate for this one. I might need a new marker. Let me see if I can find a new blue marker to help our cause. I guess purple will have to work. I don't feel like digging for a blue one at the moment. We'll just use a purple marker. That's fine. Okay, so then where do we go from the segment addition postulate? Well, we can say now that KL plus LM is greater than NL plus LP. Let's stop and think about this a minute. Okay, why can we say that? Well, KL is greater than NL, LM is greater than LP. So if you have two greater thans on one side, they're definitely going to be greater than the two lesser thans. In step 3, in this case, you're just going to say a property of inequality. A property of inequality is what you would say. Which now we can use what we have from the segment addition postulate, that KL plus LM equals KM. We could substitute KM in here in step 4 for the KL plus LM. We can now say KM is greater than the NL plus LP, which would be equal to NP. We could substitute NP in for that by the substitution property. So that also wasn't too bad. So let's go through this proof again. We'll start with KL is greater than NL, LM is greater than LP. That was given to us. And then we're going to say KL plus LM equals KM, NL plus LP equals NP. That's by the segment addition postulate. And then by a property of inequality, you can say KL plus LM is greater than NL plus LP. That's by a property of inequality. And then last but not least, by the substitution property, you could say KM is greater than NP. So that's how you would do an inequality proof. Let's go on to another proof. let's see what we got for the next one. R, O, S, T, and V. Okay. So we have angle ROV split into a total of 3 angles. So let's see, what do they give us this time? They give us that the measure of angle ROS is greater than the measure of angle TOV. So they give us that the measure of angle ROS is greater than the measure of angle TOV. What we have to prove is that the measure of angle ROT is greater than the measure of angle SOV. Okay, so we're going to draw our 2 columns again. With some statements and reasons. All right, let's start with our first given piece of information. Well, we have here what's given to us: the measure of angle ROS is greater than the measure of angle TOV. The reason for that statement, of course, it was given to us. Well, ultimately, the goal is to get to that the measure of angle ROT is greater than the measure of angle SOV. So what I think we should do next is say that the measure of angle ROT is equal to the measure of angle ROS plus the measure of angle SOT. We also can say in this same statement that the measure of angle SOV is equal to the measure of angle SOT plus the measure of angle TOV. That, of course, for statement 2 is going to be the angle addition postulate. So by the angle addition postulate, we can actually then say that the measure of angle ROT equals the measure of angle ROS plus the measure of angle SOT. And then the measure of angle SOV equals the measure of angle SOT plus the measure of angle TOV. Well, look at what both of these angles have in common. They both have a common measure of angle SOT, do they not? So I think step 3, we need to say the measure of angle SOT equals the measure of angle SOT. That's going to be by the reflexive property for step 3. That's by the reflexive property. Well, let's notice something. If the measure of angle ROS is greater than the measure of angle TOV, and then SOT is a component to both of these angles, ROT and SOV, then couldn't we say for step 4 that the measure of angle ROS plus the measure of angle SOT is greater than the measure of angle SOT plus the measure of angle TOV? Couldn't we say that then, since SOT is a component to both of those angles? We sure could. That's going to be by a property of inequality. By a property of inequality. Which then, last but not least, we could substitute the values for the sum of these angles in. In step 5, we can then say the measure of angle ROT is greater than the measure of angle SOV. That would be by simple substitution property. So let's go over this proof again here, okay? We start out given that the measure of angle ROS is greater than the measure of angle TOV. That's given to us. Well, the second statement is the measure of angle ROT equals the measure of angle ROS plus the measure of angle SOT. And then the measure of angle SOV is equal to the measure of angle SOT plus the measure of angle TOV. Those are both by the angle addition postulate. And then, of course, measure of angle SOT equals the measure of angle SOT. That's the reflexive property. So now we can say by a property of inequality that the measure of angle ROS plus the measure of angle SOT is greater than the measure of angle SOT plus the measure of angle TOV. And then last but not least, by the substitution property, we can say that the measure of angle ROT is greater than the measure of angle SOV. So far this is it for inequalities that we've done so far. We have a few more proofs, then we'll be done for the day. The next few lessons are not going to be conventional, not at all. But they are very necessary. Alright, what's the next one we're up against here? This extends out a little bit. Okay. This up here is point V. Here's X, Y, and Z. Okay. So we have a triangle XYZ with a line extended to point V from YX. What do they give us in this case? We are given, what are we given? That VY is perpendicular to YZ. We've been given that VY is perpendicular to YZ. What we have to prove is that angle VXZ is an obtuse angle. It sounds harder than it really is. This isn't going to be that bad, okay? But let's go ahead nonetheless, start with our statements and reasons. Alright, so we're given for statement 1 that Vy is perpendicular to YZ. That, of course, means it's given to us. What can we deduce from Vy perpendicular to YZ? We can deduce then that angle Y is a right angle. By the definition of perpendicular lines, we can deduce from that angle Y is a right angle. In fact, let me put that right angle marker, the perpendicular marker there to aid us. Okay. Well, where do we go from there? Step 3, we can say that triangle XYZ is a right triangle. That is, of course, by the definition of a right triangle. Which now is going to lead us into step 4, which is going to be the measure of angle VXZ is equal to the measure of angle Y plus the measure of angle Z. This is by that theorem that states the measure of an exterior angle equals the sum of two remote interior angles. Now, for step 5, we can play off step 4. We can put in 90 degrees for the measure of angle Y, right? Because it's a right angle. So we could say the measure of angle VXZ equals the measure of angle Z plus 90. That's going to be by simple substitution property. We can substitute that 90 in for the measure of angle Y. And then step 6, we can now say that angle VXZ is an obtuse angle. We could say that by the definition of obtuse angle, because as soon as you add anything to 90 degrees, you get an obtuse angle. Anything, of course, that's, if you have a 90 degree angle, as long as the next angle is less than 90 degrees, you have an obtuse angle. But we have a triangle here. There's no way that you could have another right angle or an obtuse angle. So we can clearly say for step 6, by the definition of obtuse angle, that angle VXZ is an obtuse angle. So let's go through this proof again here. We start out given that Vy is perpendicular to YZ. That was given to us. Which means in step 2, we could say angle Y is a right angle by the definition of perpendicular lines. Which in step 3 now, we can say triangle XYZ is a right triangle by the definition of a right triangle. Now, step 4, we can say the measure of angle VXZ equals the measure of angle y plus the measure of angle z. That's by the theorem that says the measure of an exterior angle equals the sum of the two remote interior angles of a triangle. So that's that theorem. Now step 5, we can substitute 90 in for the measure of angle y and get the fact that the measure of angle vxz equals the measure of angle z plus 90. That's by the substitution property, which by the definition of obtuse angle, since the angle is greater than 90, we can say that angle VXZ is an obtuse angle. So that one actually wasn't too bad either. What do I have here? I have... Good, I should only have 2 more proofs. I should only have 2 more, then we'll be done for the day. All right, what do we get next? This one's going to be a little hard to draw. We have that. This extends a little bit. Just looks funny, that's all. All right. So there's 2 merging triangles. Let's see what they give us. This is angle 1. This down here is angle 2. This right here is angle 3. Then this right up here is angle 4. Okay, so what do they give us? They give us that the diagram, given the diagram, wow, that's a big help, isn't it? That's okay, we got this. Sometimes that's all you get is the diagram. What do they actually want us to prove? They want us to prove that the measure of angle 1 is greater than the measure of angle 4. All right. So let's start there. Let's go ahead, let's draw out our columns. We have statements, then we have reasons. Okay, so we have the diagram. I don't think we need to put that in our statements. If all you're given's the diagram, you don't need to make a statement about it. I think that's kind of stupid. But what we can notice right away is that angle 1 is greater than angle 2. So the measure of angle 1 is greater than the measure of angle 2. Well, why is that? Why is the measure of angle 1 greater than the measure of angle 2? It goes back to the Exterior Angle Inequality Theorem. So the Exterior Angle Inequality Theorem. See how that theorem's actually useful now? Remember, the Exterior Angle Inequality Theorem states that the exterior angle of a triangle is greater than the measure of either 2 remote interior angles. And angle 2 would be a remote interior angle to this triangle standing up, would it not? Okay. Now, let's look at this little triangle right here. You have angle 3 here, you have angle 2 here. If you look at this little triangle, couldn't we count angle 2 as a exterior angle? We certainly could. We can actually now say the measure of angle 2 is greater than the measure of angle 3 for really the same reason. It's really going to be by the same reason. Alright? Because in this triangle, angle 3 is a remote interior angle. Angle 2 would be the exterior angle for this little triangle here that contains angle 3. So now, the reason for angle 2 being greater than angle 3 is also going to be by the exterior angle inequality theorem. Alright, so now step 3, we have angle 3 and angle 4 here, right? Angle 3 and angle 4 are vertical angles. Well, we know the measure of angle 3 would actually equal the measure of angle 4 because vertical angles are congruent. So for step 3, vertical angles are congruent. Since 3 and 4 are vertical angles, they're congruent. Now, for step 4, we can say that the measure of angle 1 is greater than the measure of angle 3. The measure of angle 1 is greater than the measure of angle 3. Think about it. If 1 is greater than 2 and 2 is greater than 3, then 1 is definitely greater than 3, right? That's going to be by a property of inequality. And then if the measure of angle 1 is greater than the measure of angle 3, well, step 5, we can now jump to the measure of angle 1 is greater than the measure of angle 4 by simple substitution. By the substitution property, we can now say the measure of angle 1 is greater than the measure of angle 4. Whoops, I don't need to write the statement, I need to write the reason. Okay, so let's go through this proof again real quick. So, all they gave us is the diagram where you have two big triangles and each triangle split into two subtriangles. And then you have exterior angle 1. We can make the first statement right off the bat that angle 1 is greater than angle 2 because of the exterior angle inequality theorem. For the same reason, we can say for our second statement that the measure of angle 2 is greater than the measure of angle 3, also by the exterior angle inequality theorem. And then we can say that the measure of angle 3 equals the measure of angle 4 by the fact that vertical angles are congruent. And then by a property of inequality, sort of like the transitive property of inequalities, you can say that the measure of angle 1 is greater than the measure of angle 3. And then by simple substitution property, you could say the measure of angle 1 is greater than the measure of angle 4. So that proof actually really wasn't that bad. We got one more, then we're done for the day. I know inequalities are very funky, especially when dealing with them in geometry. I know they were weird enough in algebra, but when you bring them up in geometry, that really tends to throw people. And when I was first learning geometry, it got me too. But I had an excellent teacher and people that helped me, so... Okay, let's see here. Another one with two triangles. Let's see what they give us here. QSV. So here's QSV. They give us, here's T, here's R, then here's a point on this line, X. All right, so here's a nice diagram with two triangles connected at point V, and then from QR it extends out to point X. So what do they give us in this case? We are given that QR and ST bisect each other what we have to prove is that the measure of angle XRT is greater than the measure of angle S. So this is going to actually be a very interesting proof. So let's go ahead and draw our columns again here. I should make them big simply for the fact that there's going to be a lot of information to cram into this. So I got statements here on the left. I got reasons on the right. Okay, so what's our first statement? Well, start with the given that QR and ST bisect each other. The reason, of course, that was given to us. Now, let's hang on here a second. If QR and ST bisect each other, what does that mean? Well, that means to bisect, it splits the segments into two congruent parts. So if QR is bisected, that means that QV is going to be congruent to RV. And then that means that SV will be congruent to VT. Right? So now we can actually go ahead and say that QV, segment QV, is congruent to segment RV. And then we can say that SV is congruent to TV by the definition of segment bisector. Don't really use that definition a lot, but here it is, definition of segment bisector. If you look at this here, okay, just take a look a second before we go on to step 3. Each of these triangles, you have so far two congruent segments. Now, what else do we observe? That QVS, that angle QVS and angle TVR, those are vertical angles, right? What do we know about vertical angles? They're congruent. So we can put congruency markers here. So that'll actually be our third statement then, that angle QVS is congruent to angle RVT. And the reason is vertical angles are congruent. Okay, now look at your two triangles. Look at your two triangles. you have a side angle and a side angle and a side congruent in each triangle. Therefore, that is actually sufficient enough to now say that triangle QVS is congruent to triangle RVT by the side angle side theorem, or the SAS theorem. All right. Now, here's the thing. Where do we go from here? Because we have congruent triangles now, which is very nice. That's going to help us immensely. I think what we should say next, we'll come back to the whole congruent triangle theory in just a minute. Let's look at angle XRT. All right, angle XRT, that's an exterior angle, right? What do we know about exterior angles, especially pertaining to the Exterior Angle Inequality Theorem? That the exterior angle is greater than the measure of either two remote interior angles. So what we can say is that the measure of angle XRT is greater than the measure of angle T. The measure of angle XRT is greater than the measure of angle T. That's going to be by the Exterior Angle Inequality Theorem. Yes, I abbreviated it, and you can do the same in your proofs. Now, we've determined by the Exterior Angle Inequality Theorem that the measure of angle XRT is greater than the measure of angle T, okay? Now let's come back to congruent triangles. If triangle QVS and triangle RVT are actually congruent, then that would actually have to mean that angles T and S would be congruent to each other. So the measure of angle S equals the measure of angle T by CPCTC. Corresponding parts of congruent triangles are congruent. Which now from here we have one final statement, that the measure of angle XRT is greater than the measure of angle S, which is ultimately what we were seeking to prove. That would be by the substitution property. Okay, so let's go over this proof again real quick. So we start out with our diagram here, two triangles side by side that intersect at point V. And then from segment QR, it actually extends all the way down to X, really giving you segment QX. But the first thing you're given is that QR and ST bisect each other. That's given. Well, by the definition of segment bisector for statement 2, we can therefore conclude that QV is congruent to RV, and then that SV is congruent to TV. And then from there, we can actually conclude that angles QVS and angle RVT are congruent to each other by the fact that vertical angles are congruent. Which then ultimately led us to triangle QVS is congruent to triangle RVT by the side angle side theorem, the SAS theorem. And then from there, we said the measure of angle XRT is greater than the measure of angle T by the Exterior Angle Inequality Theorem. Next, we can say the measure of angle S equals the measure of angle T by CPCTC. The corresponding parts of congruent triangles are congruent. And then by simple substitution property, we can say the measure of angle XRT is greater than the measure of angle S. So, really not that bad to work with. Now, the next two lessons are going to be a bit different. The next lesson itself will be about more logic stuff. So, The next lesson we'll talk about inverses and contrapositives of statements. So far we've talked about the original statement and then the converse. Well, the next lesson we're not only going to have those, we're also going to have the inverse of a statement and the contrapositive of a statement. And we're going to try to deduce information from that. Then the lesson after that, we're going to talk about indirect proofs. So I hope everyone has a great night. Take care.